we have been focusing upon the micro manipulators, especially on micro sensors and micro transducers, and the more focus is towards optical related and optomechatronics related micro transducers and micro sensors. So, we have seen different configurations of optomechatronics based micro sensors in detail. Now, we will discuss about this interferometers for micro sensing. So, as far as these interferometers are concerned, interferometers are widely used in microsensing applications due to their high sensitivity, precision and ability to detect minute changes in physical parameters. They operate on the principle of interference, where two or more light waves combine to produce variation in intensity based on phase differences. So, ideally, if we try to look into the interference, so interference based sensing is a powerful technique that leverages the principle of wave interference to detect change in the physical, chemical or biological environments. It is widely used in applications such as optical sensors, biosensors and environmental monitoring. So, one of the key aspects with reference to wave interference is concerned, interference occurs when two or more waves superimpose, leading to regions of constructive, which is nothing but an amplitude increase, or destructive, which is due to the amplitude decrease interference. This principle is fundamental in designing sensors that rely on changes in phases, amplitude or frequency. So, the optical path length and phase shift. So, interference based sensor often rely on the optical path length. So, OPL is depends upon the refractive index n of the medium and d the physical distance of at which the wave travels. So, in the case of a constructive interference, the overall configuration is this, and in the case of a destructive interference, this is a kind of a overall configuration where we could observe. Now, when we try to classify the type of interferometric sensors, so the interferometric sensors are classified based on the configuration, application and the overall construction of the system. So, in this particular interferometric sensor, based on the configurations, it is classified as Michelson's interferometer, Mach Zender interferometer and a Fabry-Perot interferometer. Now, let us see the overall construction of a Michelson's interferometer. So, this is the actual configuration of a Michelson's interferometer. So, the Michelson's interferometer is a widely used optical system in microsensing applications due to its high sensitivity to small changes in distance, refractive index of or material properties. It works on the principle of wave interference, where light beam is split in two parts, reflected by mirrors recombination to produce an interference pattern. So, if you see the overall construction of this Michelson's interferometer arrangement, here there is a laser source is there. The laser source is illuminated and it is made to pass through the beam splitter. From the beam splitter, the beam are splitted into two. So, there are two mirrors are there, mirror M1 and mirror M2, and finally, the output of it is collected in a separate screen. So, in both the cases, here we have considered two mirrors, mirror M1 and mirror M2. The mirror M1 may be fixed and mirror M2 may be movable based on the objectives related to displacement. So there will be a kind of a movable, there will be a kind of movement in this M2 mirror. Appropriately, we get a different interference pattern. Okay. So in order to give you a better understanding on the schematic, this is how the overall configuration of the Michelson's interferometer looks like. So it has mirror M1. So ideally it starts with the light source. From the light source there is a beam splitter. Through the beam splitter, the beams are splitted into two, which is mirror M1 and mirror M2, and then from the beam splitter, so we have a reference beam which is taken from mirror M1 and there is a reference beam from mirror M2. These reflected beam from both mirror M1 and M2 are superpositions, finally ending up in a kind of a interference. So ideally a Michelson's interferometer consists minimally a mirror M1 and M2 and a beam splitter M. As the source S emits light that hits the beam splitter surface M at point C, M is partially reflective. So a part of the light is transmitted through point B while some is reflected in the direction of A. Both beams recombine at point C to produce an interference pattern incident on the detector at point. If there is a slight angle between the two returning beams, for instance, then an imaging detector will be recorded a sinusoidal fringe pattern. If there is a perfect spatial alignment between the returning beam, then there will not be any such pattern, but rather a constant intensity over the beam depend on the differential path length. So this is the overall configurations which is being used with reference to a simple Michelson's interferometer. These Michelson's interferometers are efficiently used for displacement measurement, position measurement and pressure measurement. In some cases, it is effectively used for vibrational measurement also. Okay. Now there is one more type of interferometer which we call it as Fabry-Perot interferometer. This interferometer makes use of multiple reflection between two closely spaced partially silvered surfaces. Part of the light is transmitted each time the light reaches the second surface, resulting in multiple offset beam which can interfere with each other. The large number of interfering rays produces an interferometer with extremely high resolution, somewhat like the multiple slit of a diffraction grating increases its resolution. The interferent fringes for concentric circles are, this is the overall construction where we have an incident light. This incident light is made to pass through a multiple reflection between the partially silvered glass, and through this multiple reflected rays are out of phase by a constant increment. Now the interference fringes for the concentric circles are available. The higher order towards the center is called as M+1 and the lower order is called M. The condition for maximum is governed by 2D cos alpha equals m lambda. Lambda corresponds to the wavelength and alpha corresponds to the incident angle and d corresponds to the spacing. Apart from the Fabry-Perot interferometer, there is Mach Zender interferometers are also a type of interferometer that measures the relative phase shift between the two collimated light beam. It consists of two beam splitters and two flat mirrors. All the mirrors and the beam splitters are adjustable for the alignment and the back surfaces are multi-layer anti-reflected coating. A red laser diode is used as an optical light source. This wavelength is visible and provides a significant advantage for the alignment of the mirrors and the beam splitters. An incoming laser beam of coherent light splits into two identical beams of equal intensities at the beam splitter BS1. Each of these two beams travel a diffracted path until they combine together at the BS2 before arriving at to the detector or a charge coupled device. The difference in the distance and the medium traveled by each beam creates a phase difference between them. This phase difference creates the interference pattern from the second beam splitter BS2 up to the CCD camera. This phase shift is recorded by a digital system using a CCD camera. So, this is a kind of a interference pattern which is basically observed, and since here a helium neon laser is used, these helium neon lasers are converged using a planar convex lens. Then using a kind of a BS1 and BS2, appropriately the beams are manipulated and collected to form a kind of an interferometric pattern as shown over here. Now, as far as application perspective point of view, so these interferometers are ideally used for precision distance and displacement measurement, surface profiling and optical testing, vibration and strain measurement, medical imaging and diagnostics, biosensor related applications. In a macro level, it is used for satellite and spacecraft navigations. Interferometric telescopes are widely used for certain amount of applications. Then there is an optical coherence tomography, and optical fibers are some of the key applications using these particular interferometers. Now, as far as micro robotic perspective point of view, these are the 4 applications which caters for micro robotic applications. So, there are several research which focus upon using an interferometer for micro robotic applications towards these kind of integrated for these specific applications. Now, let us talk about an optical fiber sensor. Optical fiber sensor is considered to be one of the key successful sensor which is used for condition monitoring of systems, as well as it is also widely used for micro sensing related applications. So, as far as these optical fiber sensors are concerned, it utilizes light propagation in optical fibers to detect changes in the environmental conditions. These sensors are highly sensitive and immune to electromagnetic interference, and it is suitable for remote sensing related applications. Let me just introduce you to the configuration of this optical fiber based sensor. So, in this optical fiber based sensor, we have a light source, there is a core which is available, and then there is a clad is there. So, through the core, the light is made to pass through it. So, there is going to be a total internal reflection which exhibits in this particular process, and the core has a high refractive index and the cladding has a kind of a low refractive index. So, since the core has a high refractive index, it results in a multiple internal reflection of this particular light, and appropriately this entry of the light is governed by a quantified parameter which is called as a numerical aperture of the optical fiber. Now, as far as these operation of these optical fibers are concerned, or micro sensing of these optical fibers are concerned, based on the sensing characteristics, these optical fibers are characterized for temperature sensing, pressure sensing, strain sensing, and chemical sensing. So, let us discuss the different configurations of sensing or micro sensing using an optical fiber in detail. First, let us discuss about a temperature sensing. So, as far as temperature sensing is concerned, so not only the measurement of temperature in the positive side, there is a need to measure the temperature in the negative side also. That is, development of sensors in the cryogenic for sensing the cryogenic environment is also one of the key aspects which we may need to look into it. So, in this particular process, so in most of the cases, in majority of the cases, optical fibers are directly used. However, in some specific cases where these optical fibers are coated with a certain amount of materials, so that these materials has a capability to sense the temperature even in the low temperature condition. So, since optical fiber based sensors offers a robust and a versatile solution for temperature measurement across various environments, it is used both as an extreme high and low temperature sensors. As far as this fiber optic high temperature sensors are gradually replacing the traditional electronic sensors due to their small size to electromagnetic interference, the remote detection, multiplexing and distributed measurement advantage. Optical fibers with smart material coating, allowing them to withstand temperatures greater than 600 degrees Celsius. So, the shape memory alloy coated optical fibers withstand extreme high and low temperatures. So, if you see the overall configuration or if you observe the overall configuration of these shape memory alloy materials. So, in these shape memory alloy materials, like we classify these shape memory alloy materials based on the type of actuation behavior. So, actuation behavior is nothing but like with reference to the actuation, like there is going to be a kind of a change in displacement which exhibits. Now, that is, let us consider, so I have a kind of a strip. So, this strip will be highly sensitive to this particular temperature which we call it as an actuation temperature. So, based on the material composition, there is a change in the actuation temperature. Like if you try to consider a copper based shape memory alloys, see the copper based shape memory alloys has a quite a good amount of efficiency in the both in the low temperature conditions, especially up to minus 270 degrees Celsius, and it has a capacity, it has an actuation temperature in the range of 150 to 250 to 350 degrees Celsius. Whereas conventionally, when you try to see the nickel titanium based structures, these nickel titanium based structures has a potential actuation temperature ranging from 80 to 130 degree Celsius. Now, let us take an actual example where a shape memory alloy has been coated on an optical fiber like and it is used for sensing an extreme condition. So, already we have we will be studying about the shape memory alloys in detail. These shape memory alloys are coated on an optical fiber which actuate the fiber due to a temperature range, and the change in the temperature induces a strain on the SMA. So, like which in turn bends the fiber. Such bending of the fiber results in optical signal attenuation. At high temperature, SMA straightening, the shape memory alloy will straighten the fiber, whereas at low temperature conditions, we can see a kind of a bending which happens. So, ideally, like so we have seen a lot of functionality about a shape memory alloy. So, this is quite encashing the shape memory alloy as a sensing behavior. Shape memory alloy sensing behavior with reference to low and high temperature conditions has been investigated by depositing this shape memory alloys on an optical fiber and appropriately sensing the behavior of it. So, the overall construction looks something like this, where we have a laser source and the detector which is available, and this is a kind of an SMA coated fiber. By changing its characteristics appropriately, we can monitor the behavior. In fact, this is a kind of a cryogenic sensing which has been deployed. So, in this cryogenic sensing, so we have a SMA biomorph. So, in this SMA biomorph, the SMA coated optical fibers are integrated appropriately. So, as far as SMA biomorph is concerned, so we have discussed this in the earlier modules also, where how these SMA biomorphs were developed and how these SMA biomorphs were deployed for different applications. Now, like when we try to integrate this SMA coated fiber along with SMA biomorph, this will improve the sensitivity of the system. So, ideally at room temperature, this will be the configuration. When it is exposed to a low temperature, it takes a curled shape. Now, once again, when I try to shift it back, it comes back to this shape. So, this sensing this cryogenic temperature is one of the challenging tasks with reference to conventional sensors. However, with optical fiber based sensor are considered to be a superior substitute due to their immunity to electromagnetic interference and power fluctuations. Shape memory alloy coatings on optical fiber certainly improve the sensor response. the displacement due to phase change of SMAs during exposure at extremely low temperature. The phase change induces thermal strain on the fiber, leading to change in the refractive index of the core and cladding, which results in the intensity change of the optical output signal. The integration of the SMA bimorph with SMA coated fiber significantly enhances the displacement due to the enhanced induced strain, which leads to attenuation of the optical output. Such attenuation of output signal relates to the low temperature sensitivity of SMA coated optical fiber, and this is a kind of an LDS sensor which is deployed to investigate the overall actuation which is happening on an SMA coated optical fiber in the liquid nitrogen environment. Now, we will discuss about the optical fiber based pressure sensor. So, as far as in this optical fiber based pressure sensor is concerned, this is the source and this is the detector. The optical fiber is integrated with the diaphragm and pressure is induced on the diaphragm. So, the optical pressure sensor consists of three components: the sensing head with a metal diaphragm, a cable with two fibers, and an optoelectronic system with LED and photodetectors. The light from the LED source is allowed to be transmitted through one fiber, and the reflection from the metal diaphragm is taken through the second fiber. This reflected signal is received by the detector and the other signal conditioning circuit. So, the diaphragm displacement depends upon the extent of the applied pressure which is available over there. So, the interesting part in this is such kind of systems are highly compact and it is completely free from the electromagnetic shielding, and most important aspect is like these are kind of reliable systems which can be used for a continuous monitoring of continuous monitoring. This is a highly sensitive fiber based system. So, in this fiber based system, so what we have is like in order to improve the sensitivity of an optical fiber, Bragg grating sensors are employed. So, Bragg grating sensors are nothing but gratings are inscribed inside the optical fiber, where there is a kind of a core which is established over here, and then there is a propagation core mode which exists, and then it is concerned with the transmitted signal. So, light is incident on it. It is a kind of a reflected signal and a propagating core signal and a transmitted signal. These Bragg grating signals are optical sensors that utilizes the principle of the fiber optic and Bragg reflection to measure the strain, temperature, pressure and other physical parameters. The FBG is a periodic variation in the refractive index of a fiber optic core created using an ultraviolet light. When broadband light is sent through the fiber, a specific wavelength, that is a Bragg wavelength, is reflected while the rest is transmitted. This Bragg wavelength is given by lambda b equals 2n efficient lambda, where 2n is the effective refractive index of the fiber core and del is the grating period. So, the change in the strain, temperature or pressure alter the overall effect and the lambda, causing a shift in the Bragg wavelength, which can be measured to determine the applied physical change. This applied physical change can be either a pressure, or in certain cases it might be a strain, in certain cases it might be a temperature also. Now, let us take an example with reference to a strain sensor. So, in the case of a strain sensor, let us consider, so we have an input signal. This is the intensity, lambda. This is the input signal or the incident signal. So, if we try to quantify the grating period, this is del N A N core and N effective grating period. So, if this is going to be the input light, appropriately we will be getting two different response. One response is the reflected light and the other response is the reflected light. So, it is a kind of a intensity. This is from the reflected light. In the case of a transmitted light, so a fiber optic strain sensor here is used for the structural strain measurements. So, to create the actual strain sensor, the optical fiber is inscribed with the FBG grating, which is this is basically a pattern of material interference which reflects the light different from the rest of the fiber. So, that is, so ideally when we try to look into the overall sensing capability of an optical fiber. So, one way of sensing can happen through an intensity modulation, other way of sensing can be happen to wavelength shift. So, with fiber Bragg grating we can deploy the wavelength shift, however without fiber Bragg grating, so we will be having a kind of an intensity modulation. So, the material interference, the slices are placed at certain intervals when the fiber is stretched or compressed and it is therefore subjected to positive or negative strain. These intervals change when the fiber is stretched, it lengthens and spaces gets bigger and vice versa. The FBG sensor reflects a specific wavelength of light lambda b based on the grating period del and a refractive index NEFF. So, when the strain is applied, the del changes causing a shift in the reflected wavelength, which can be represented with this particular equation. This wavelength shift is proportional to the strain applied to the fiber. So, ideally based on the reflected signal and based on the transmitted signal, appropriately we can have a kind of a idea on the measurement of the strain, or we can continuously monitor the strain what we are looking for. So, when we try to look into the distributed sensing of an optical fiber sensor, these optical fiber sensors has a capability to sense the different positions in the different optical region. So, the basic operation of a distributed fiber sensing requires an illuminating a length of an optical fiber by a repetitive pulse of coherent light. The equipment used is referred to as an interrogator. So, each pulse is subjected to a transmission delay as it works its way along the fiber. At individual position, throughout the fiber is highly attenuated, backscattered signal arises and will return to the source. And in known time, there is a kind of a propagation delay which is determined by its time of flight measurements. So, overall, like in a 40 kilometer range, we can use a strain measurements, a temperature measurement, a distributed measurement and an interrogated measurements. So, like with reference to micro robotics perspective point of view, if we are working on a particular domain where we are trying to actuate such kind of micro robotic sensors in this particular domain, so these kind of sensors are efficiently used for condition monitoring of these entire domain. So, appropriately the actuation behavior can be taken care of. Now, let us see how optical fiber chemical sensor uses optical fiber to detect and measure the presence of a specific chemical substance. So, a sensor operation based on the changes in the optical properties of light such as intensity, wavelength, phase or polarization when exposed to a specific chemical such as absorption based sensing, which means a chemical absorbs a specific wavelength of light altering the transmitted signal. Fluorescent based sensing, a fluorescent chemical marker emits light at a specific wavelength upon excitation. Surface plasmon resonance, a change in the refractive index near a metal coated fiber surface which affects the light propagation. So, in this method, the lifetime is obtained from the phase shift between the emission signal from the chemical sensor and the excitation signal used. Currently, some of the analytical instruments that enable the measurement of a large number of analytes such as pH, carbon dioxide or oxygen are known. So, this is a kind of an analyte which is being kept in a selective membrane. So, as and when there is a kind of absorption which happens based on the selective membrane, there is going to be a change in the overall characteristics. So, now, if we try to look into the overall application of it, so these kind of optical fiber sensors are efficiently used for structural health monitoring, aerospace and defense applications, biomedical applications, environmental monitoring, oil and gas industry. So, one of the key advantage or some of the key advantages of this optical fiber sensors are it has a high sensitivity and high accuracy. It detects a minimal changes in the strain, temperature, pressure or chemicals. As far as immunity to electromagnetic interference perspective point of view, it works in high voltage and high radiation environment. It is a lightweight and compact, suitable for aerospace, medical and industrial applications. It can be used for long distance sensing as well as a short distance sensing. So, it can transmit signal over a kilometer without any signal degradation. As far as multiplexing capacity is concerned, these multiple sensors can be integrated along with a single fiber. So, it has a good resistance towards corrosion, especially as I had mentioned earlier. It is highly useful for underwater oil and gas and space applications. Remote and distributed sensing, which is useful for monitoring large infrastructures like bridge, tunnels and pipelines, etc. As far as micro robotics perspective point of view, such kind of optical fiber sensors are efficiently used for condition monitoring of the overall working window of these optical fibers, and in certain cases in order to measure the strain and the temperature, such kind of optical fibers are employed. So, just to give you a overview, so we had discussed about the different concept of microsensors. We have introduced the microsensors and micro transducers. We have given an exposure. So, this lecture basically gives you an exposure about the overall configuration of the microsensor development and how the microsensors are deployed with reference to different parameters. So, if we try to categorize the microsensors, there are two key elements which exhibits in a microsensor. One is a microsensing element and the microtransduction element. Based on the application, so the microsensing element and the microtransduction element are selected, and then the working principle of the microsensors. This is a template for a working principle of the microsensor about the different sub elements which are available in these microsensors. Then the classification of the microsensors, basically with the reference to radiation, with reference to thermal microsensor, magnetic microsensor, mechanical microsensor and chemical microsensor. So, the different transduction element, the different sensing elements are discussed, how it is used for robotic applications, about the pressure transducer, piezoelectric transducer, a capacitive transducers and an inductive transducer, fundamentals about an ultrasonic transducer. So, then we had a discussion about the integration and the signal processing. We had a discussion about this optomechatronic system design, about the overall evolution of this optomechatronic system design and how these what are the different elements of optomechatronic system design, how these optomechatronic system designs are classified and how it is effectively used for micromechanical applications, So, these are the list of functions of different optomechatronic systems and their applications. How optomechatronic systems are deployed in robotics. As far as optomechatronic system perspective point of view, it is efficiently used for displacement measurements as well as for the kind of force and strain measurements. Some of the components of optomechatronic systems are discussed in detail, and then this is a simple example where a kind of a micro optomechatronic system is integrated with the piezoelectric actuators, and the overall transformations are studied. Then the different applications of optomechatronic systems, about the configuration of an LDS sensor, about the different techniques which are involved with reference to optical displacement measurements, which includes the triangulation based sensor, the interferometric displacement sensor, a confocal sensor, a time of flight sensor, and an optical encoders. Then there is a discussion on the triangulation sensor, an interferometric displacement sensor, a confocal sensor, and a time of flight measurements, how a shadow projection sensor is used for visualizing the moving objects in a system. So, which has a potential applications in micro robotic related application, especially for magnetic actuation, nanoparticle integrated, micro and nanoparticle integrated actuations, etc. So, we also had a discussion about this optical encoders, the overall applications, influence of light intensity modulation in sensing, about the different concepts of light intensity modulation, classifications of light intensity modulation. We had a discussion about optical fiber sensors configurations, and in how interferometers are used for micro sensing. Different types of interferometers, which includes a Michelson interferometer, a Mach Zender interferometer, and a Fabry-Perot interferometer. This is the overall construction of a Michelson interferometer and how these are being effectively deployed for different applications. And then an optical fiber-based sensors, temperature sensors, shape memory, a smart material coated temperature sensor for cryogenic temperature sensing, as well as the high temperature sensing applications has been discussed, and optical fiber based pressure sensors has been discussed, and the overall fiber Bragg grating, application of fiber Bragg grating in strain sensing related applications. If we consider a big environment, so these kind of distributed optical fiber sensor are effectively used for sensing different levels. Then about the chemical sensors, different applications, advantages of this optical fiber, and these are the references which we have used for preparing these slides.